Alright, now that we have some basic measurements and how to work in the lab, we're going to start Chapter 2 and really start to look at the atomic structure and the arrangement of the different elements on the periodic table. So some of the goals for Chapter 2, looking at the modern theory of atomic structure, so you should be able to explain some of the major assumptions of atomic theory, and then you should learn how atoms of different elements differ. So you should be able to explain the composition of the atoms according to their number of protons, neutrons, and electrons. You should be able to describe the atomic mass and how isotopes differ from one another. Then we'll spend some time talking about the periodic table and how the elements are arranged on the table and some of the major trends of the periodic table. So atomic theory really started way back with the Greek philosophers. Aristotle believed that matter could be divided indefinitely. However, Democritus argued that there was a limit, that there was a smallest particle that you could get down to. And so when he defined his smallest particle, he described this as being the atom, as being the smallest identifiable particle. So the word atomos from the Greek language means indivisible. So the definition of an atom then is the simplest unit that an element can be broken down to while still maintaining its identity. So it's the smallest fragment or particle that you can get that still constitutes the elements that are represented on the periodic table. So here we've got helium, lithium, carbon, and titanium. You can see that the different elemental forms of these different things have different sizes. So they range from being very small, like helium, to very large, like titanium, and even larger for something like lead. And we'll see the different components that make up the atom are going to help constitute these size differences. So atoms are extremely small. So this is an interesting factoid. If you have 1 teaspoon of carbon, it has 3 times as many atoms in it as the Atlantic Ocean has teaspoons full of water. That's how small the atoms are. So last time we talked, we said that there's 114 elements that have been discovered. 90 of these occur naturally, and 24 are produced artificially. So we've already seen our periodic table, and we know that there are 118 elements that are predicted by the periodic table. 91 of these occur naturally. The rest of the known elements are produced artificially, and there's still a few elements that have not been discovered yet. So there will be some familiar elements that you'll have heard of before, like iron and tin and carbon and oxygen. And then there'll be some unfamiliar elements that you'll learn about in the class. Some of these are niobium, rhodium, thulium, and californium. So Dmitri Mendeleev was the first person to put together a periodic table of the elements, and he argued that the elemental properties are periodic functions of their atomic mass. And he first published his first table of the 63 elements that were then known. So you can see we've discovered many elements since 1869. He was able to predict for spots of undiscovered elements at that time based on their atomic masses. However, as time went on, in the early 1900s, the Danish physicist Niels Bohr was very instrumental in helping develop the concept of atomic theory. And so this is one of the elements that you'll be learning about in the class, that atoms are actually composed of smaller particles. And these 3 major particles are called neutrons, protons, and electrons. And in fact, even these smaller particles can now be broken down into smaller particles. So when we're thinking of Democritus coming up with this theory that the atom structure is the smallest divisible structure of a unit, we can say that for the element. Once you break down an atom into its smaller components, it no longer retains the physical identity and the properties that define a specific element. So elements are defined specifically by the number of protons and the number of electrons that they carry within them. So you need a full atom to give you any one of the elements. However, scientists are now discovering, though, that you can break down the atom into these smaller fragmented particles, and that you can even break down things like protons and neutrons into even smaller components or fragments. So It's not clear really yet whether Aristotle or Democritus was correct that there is some indivisible component that you can get down to that makes up the fundamental units of all matter in space and time. So these are some fundamental questions that physics is trying to address now. But for our discussions, we're mainly just going to be interested in these smaller particles, the neutrons, the protons, and the electrons, and how they form atomic structure, and how these atomic structures then define the major characteristics that we see in the periodic table. So all of matter is composed of atoms, and atoms have a nucleus which contains the protons and the neutrons, and then the nucleus is surrounded by a cloud of electrons. And so this is just showing this cloud of electrons in a three-dimensional scale, so you just have this graph that's placed upon it. So the density of the small dots then is related to the probability of finding an electron at these positions at any one time. So you can see that the electrons have higher probability of being closer to the nucleus of the atom, where the protons and the neutrons are going to be held. The protons and the neutrons are going to be pretty stable and held in the center. The electrons then are orbiting around the outside of the neutrons, just like the planets will orbit around the sun. Except we're going to see that the orbits and the shell patterns that they take are not generally these elliptical patterns that are kind of shown in this diagram. They're more complex than that. So both protons and neutrons have a mass that's close to 1 AMU, or atomic mass unit. And so this is kind of a derived unit that is given based on the mass of the proton and the neutron. And so their mass unit in grams is also shown here. And so this is kind of our metric scale that we can compare to. And so we have a conversion that we can make between mass and grams and atomic mass units. So the atomic mass unit is going to become very useful, though, because it's going to start building this fundamental concept of formula mass or molecular mass. And we'll be able to use that in a very useful way when we start thinking about chemical equations and quantities of different substances that we will need to make reactions go forward. One thing that you should notice here is that the weight of the proton and the neutron are pretty big, and they're both listed as 1 atomic mass unit each. But when you look at the electrons are really, really small. So they're 10 to the minus 4th. So they're 1,000 times smaller than the protons and the neutrons. And so they don't really contribute much to the atomic mass. And so they're oftentimes just dropped entirely from the atomic mass equation, that we only really derive the atomic mass from the number of protons and neutrons that are present. The number of electrons really doesn't affect the weight or the mass of the atom very much, and so we don't really count it in the mass. The other thing that you should notice about these different fundamental units of the atom is their charge. So the protons are positively charged, the neutrons are neutral, so neutral neutrons, and the electrons are negatively charged. And so there's an attractive force that happens between the protons and the electrons because opposite charges are going to attract each other. And so this is a fundamental concept that you should pick up about the atoms.